All right. Good afternoon, everyone. So last time we were working our way through the derivation of backpropagation for our two-layer neural network. So the first thing we did is we looked at the case where we had all scalar variables and a batch size of 1. And we went through first the forward pass equations, which just describe what happens to the data as it makes its way through the network, from the features and labels and the parameters all the way to the loss. And then we used backpropagation, which moves from right to left, to finally derive the derivatives of the loss with respect to the parameters, because those are the things we need for gradient descent. And what we did is we just started at the end. We did dj dzo. That is just the derivative of our final equation, dependence of our loss function on our scalar output score. And then to do dj dah, we did dj dzo times dzo dah. And we reused the computation that we just did over here. And then we had one new computation to do, which we can figure out from this equation. And from there we saw dzo dah is just w naught. We compute that, and we move on to dj dzh, which we do via dj dah times dah dzh, again using the chain rule, and so on. And so by using this procedure, we kind of worked our way through, and we were able to get all the derivatives we needed. Then we considered the more realistic case where we have several items in our batch. So we have several features, several labels. And in this case, things got a little bit more complicated because for particular steps, we had to use the multivariate chain rule. In order to figure out which steps use it, we have to take a close look at our equations. So for example, all of these steps here, they don't need to use it because essentially when we look at one element in this batch here, it depends only on a single element in this batch, not all the elements in that batch. And so for that reason, we don't have to use the multivariate chain rule there. But when we get down to, let's say, dj dbo, we had to consider that bo affects all these different output z's in the batch. And so when we do dj dbo, we have to use the multivariate chain rule because it's sort of like there's a bunch of different elements there that information flows through. So in this equation, we're summing over those different paths, the different batch elements I. But then otherwise, the equations are the same as on the previous page. So that's what we saw in this intermediate difficulty case. Any questions on that last case? Okay, so then today we're going to start with the full method, which uses vector valued variables. So now our output scores are vectors. We have a batch of B of them. The hidden activations are vectors. The hidden scores are vectors. And likewise, we have weights that are matrices and intercepts that are vectors. So these are the equations for the forward pass. This is what we've seen before. But it's important to realize that still some of these operations, like this one, apply element-wise on the vectors. So like in this vector, the first element is only a function of the first element of this vector because this activation here operates scalar by scalar. It's what we call a component-wise operation. So when we do backpropagation, first of all, we're going to look at scalar calculus. So we're always going to be computing derivatives with respect to scalar values, never vectors. So for example, we would start out by saying, okay, for this stuff here, we're going to look at a single element I in the batch. And moreover, for that vector, we're going to look at a particular element k within that vector. So that's going to be ZO IK. And so then the first question is, what's the derivative of the score with respect to ZO IK? So since we're looking at a particular element of the batch, we don't have to consider the sum. We can just focus on the I that we're looking at. And moreover, we look at a particular element in this vector here. And that will give us a particular expression depending on how we choose J. I'll go over a couple cases in a couple slides. So once we do that, we move on to DJ DAH, but now we're going to consider just one particular element I in the batch, and we're going to consider one particular element, we're going to call it L in that vector. So this is DJ DAH IL. And so the first question is, okay, do we have to use some sort of multivariate chain rule or not? So we can answer that question by asking another question like, okay, if I focus on one of these elements, the Lth one, does that affect all of these Z's or just a single Z? And also we're focusing on a particular I. Does that affect all of these I's or just a particular one? Okay, so we saw last time that if I focus on a particular batch element I here, that only affects a single batch element I here. So from the perspective of the I's, we don't have to worry about multivariate stuff going on. But if you look at this equation here, and you say, okay, for a particular element within this A vector, the Lth one, does that affect one or more than one element in this Z vector? So let me see, is Nathan Becker here?
Yeah.
All right, so what do you think?
I think it would affect all of them because the matrix.
Exactly. Yeah, so we have a matrix here. We're looking at the Lth element in this. That is going to multiply by the Lth column of this matrix, which in general will have non-zero entries all the way down that column. And so that will affect all of the elements in this vector here. So we really do have to consider some sort of multivariate chain rule because this scalar element that we're investigating is really affecting all the elements in this vector. So if we denote the elements across that Z vector here, we'll use K to go down that Z vector. When we do that multivariate chain rule, we'll have a sum over K. Okay, but beyond that, it's going to be DJ DZO IK. So I is matched to here. K is running over all the elements. And then we're going to have DZO IK divided by DAHIL. So for that, we need to look back at this equation. So we're saying, let's fix the kth element in ZOI, and let's take the derivative with respect to the Lth element in AHI. And so for that, we can just, okay, so that is going to be affected by the kth row and ith column of this W matrix. And so when we focus on this scalar and this scalar, there's really just a scalar element multiplying them. And so finally, this is what you get for the derivative. So when you break it down, it's really not too bad. All right, questions on this part of the chain rule or the back propagation? Okay, is that sort of making sense? Okay. All right, what about dj dzhil? So here, we're going to use these a's as the intermediate variables to break it up. So we're going to have, so I guess the question is, all right, if I consider a particular element here, I think I'm calling it L, how does that affect all the elements here? Or, sorry, does that affect all these elements or just a single one? So let's see, is Vincent Lin here? No? Okay, what about Likith Narankurthi? Yeah. So what do you think? If I focus on one element here, does that affect all of these elements or just a single one?
I'm guessing one element.
Yeah, so for that, we look at this equation. If I look at one element here, it only affects a single element here, and it's the same one. If I look at the lth one here, it's the lth one here, because this operates component-wise. Okay, so that means that when we consider this chain rule, we don't have to worry about any multivariable stuff. So dj dzhil is dj dahil times dahil dzhil. So, and this last part here, that's just the derivative of this scalar activation function, which we can compute. We know what it is. Okay, so that gives us all of these derivatives. Any questions on those? All right, so now let's work on these. So we have a vector here, BO, but we're going to focus on the kth entry of it only. And so the first question is, all right, so if I focus on the kth entry here, how many things do I have to worry about in the middle? So first of all, do I have to worry about multiple i's? So let's see, is Colby Hiralal here? Okay, what about Siyu Huang? Okay, so Siyu, if I focus on the kth element here, do I have to consider several i's here? Several batch elements I? Yeah, I have to, because this affects all the elements in the batch. So I definitely have to consider multiple batch elements, and so in the chain rule, I'll have a sum over I. Okay, what about another question? If I focus on the kth element here, do I have to focus on all the elements in this z vector, or just the kth element? And so, I don't know, let's see, is Vasilios Konstantakos here? No. What about Ashton Keller? Yeah.
Can you ask the question again?
Yeah, so if I'm focusing on the kth element here, do I have to worry about all the elements here being affected or just the kth element there? And how do I determine that?
I guess I'm not really sure, because I know your Z vector, every element of Z is affected by DD, so.
Okay, so we just need to find the equation that unites those two things, and that would be this equation. And so now we're saying, like, if I change only the kth element here, does that affect all the elements here?
Just the kth.
Just the kth, exactly. So that's a nice simplification. So that means when we do that chain rule, we're doing dj dbok, but we know that that just affects one of these, the kth one, although it does affect all the different i's. So here we have dj dzo ik, where this k is matched to that k. And then over here now it's dzo ik dbok. And so for that derivative, we look to this and we see, oh, that's pretty easy. That derivative is just 1. Okay. Okay, so that's how we figured out this part of the chain rule. Okay, any questions on how we did that? Okay, what about focusing on a particular element in this matrix? So we're going to look at the kth row and lth column. And so if I'm focusing on one particular entry in this matrix, first question is, does that affect multiple batch elements I here? Or just a single one? Yeah, it affects all of them, right? These guys affect all the batch elements I, so that means we will need a sum over I in the chain rule. Does that affect multiple elements within that vector? What do you think? So I'll ask this to Pava and Etha. No. What about Jake Chang? Yeah. What do you think? So I'm looking at the kth row and lth column in that matrix. Which element is affected here, or are they all affected? Yeah. Okay. So here we look to this equation. We're looking at one particular element here. So if we're looking at the kth row and lth column, that will only affect the kth row here. And then so, great. So that means when we do this, dj, do, dwo, kl, we only need to look at the kth row, but all batches. And over here we havedzo, ik, dwo, kl. So, okay, so I guess to visualize this, we're looking at one entry here. We are looking at then the corresponding, we're looking at one element here, we're looking at one element here. We know that this element within the W will multiply only one element in that A vector, that is AHIL. And so that gradient is pretty easy to compute. And that finishes out this step. Okay. The other steps over here are almost identical. It's just that rather than using this as the intermediate node, we use this one. But the structure of these equations are the same. So everything happens, it's just with the hidden nodes rather than the output nodes. Okay, so we basically have made our way through, and we have all the equations we need now for back propagation. Although so far they're expressed using summations and individual elements of these matrices and vectors, which is not really ideal for implementation, because in implementation we would not want to write for loops over all this stuff. We would ideally like to re-express everything in terms of matrices and vectors, and then just do matrix vector multiplies. And so that's what we'll do in the next slide. But for now, are there any questions on these equations? Okay. All right, so the next thing is just to rewrite the previous page using matrices and vectors. So the first thing we're going to do is say, well, how do we express all of these batch elements as a matrix? Well, we're going to do this the same way we've done it all the way since Unit 1 or Unit 2. Basically, we want that in our matrix of features, the samples in the data set manifest as rows of that matrix. So I, which is always going to be our sample index, that will come down the rows of X. So we're doing that just for consistency with how we've done it throughout the course. And so that is manifested here. So here we're writing X with a transpose, so these would be the rows of X because they get transposed. And these are the different feature vectors in our batch. Okay, is everybody with me on that? All right, and then we want to make sure all the matrices are consistent with that. So so basically all of these guys have a batch index in them. So I is going to be coming down the rows of all of these matrices. So they're all defined the same way. Then, once we make that decision and we want to rewrite this in terms of matrices and vectors, essentially we're just going to take this vector and we're going to imagine stacking several i's to the right of it. And then we're stacking severals here and so on. But when we do that, you can see that I is going across the columns, which is different from how we constructed the X matrix. So we just need to transpose it. So essentially, that all of these quantities just have the transposed matrix versions to be consistent with this. Okay. So is that part making sense? All right, so then one other question is, well, what about this? So this guy, what we're going to do is we're just going to stack identical copies of this. So one way of taking that vector and turning it into a matrix with identical copies is just to multiply that column vector by a row vector that contains all ones. So this is a row vector of length b that contains all ones, and it's a row vector because of that transpose. So this has that form like this, and this has the effect of just copying that BH to all the different columns of a matrix. And so that's how it express that part. Okay, so we basically matricized this equation. What about this next one? Well, again, we're just going to stack the columns of those. And so we could write it like this. That would be direct. Or if we didn't want to have transposes everywhere, we could just remove transposes on both sides, and that's where we get that. Again, this function just is something that operates independently on every element of its input to get the corresponding element of its output. Okay. To handle this equation, we do exactly what we did with this one. And so that one ends up having the same form. And I think this last one, nothing changes. That's just as it was. So the next question is, how do we rewrite these equations? So it's really not too bad. It's just a matter of figuring out where the different indices are placed. So for example, here we want to turn this into a matrix where I would go down the, we want to turn this into a matrix where I is coming down the rows, and then this other index, which is going to be L, goes across the columns. Then for compatibility with that, I would be coming down the rows of here, and then the other index, which happens to be K, is going across the columns. And then for compatibility with that, as we go down here, K must come down the rows, and then the other index, which is L, which matches this L, would go across the columns. So now we can kind of see, okay, that would just be A, the version of A with I going this way and L going this way. That's just the full A matrix, no transposes. And so this scalar gradient here, I'm writing here as a vector or matrix gradient. This is a matrix valued thing whose ith row and lth column is just this. All right, and then the other ones are similar. This is just matrix valued dj d matrix z. Looks like this. And then if you look at this, this is just the WO matrix because K is going down rows, L across the columns, and that's how we set it up. So this is just the WO matrix. And this last one is a little different because this is not actually a matrix multiply. We have IL, IL, IL everywhere. So really, this is we're taking two matrices, and we're multiplying the first element here times the first element here to get the first element here. Then the second one multiplies the second one to get the second one, and so on. So that's not a matrix multiply. That's called a Hadamard product, a pointwise multiply. And usually it's notated with a circle with a dot in the middle. So that's pointwise multiplication, element-wise multiplication. So that's what we would need for this step. Is everybody with me so far on these? Okay, any questions? All right, and the other ones are basically the same. So k is coming down the rows of that vector. So now we need to be careful. We have, when we do this, we need k to be coming down this way, and then the summing variable I going across this way. So now you can see that sort of conflicts with how ZO is set up, so you actually need the transpose there. So here's the transpose. And then you just want to multiply by a vector that is 1 for all elements. So here we have our ones vector of length b. And so this is going to be identical. And then the last thing to talk about here is we have a matrix where k is coming down the rows, L going across the columns. This has to be the same, k going down the rows. Then the other variable, I, must be going across the columns. And then I down the rows and L across the columns. So given that setup, you can see this is just the Z matrix. And then this part is just the AH matrix. So, oh, did I miss a transpose? Oh, yeah. Sorry. This is transposed because the Z matrix usually has I coming down here and K going across here, but we swapped it. So we have here a transposed Z derivative matrix and then the A matrix. Okay, so that now gives us some really nice, clean equations to implement everything. And so you could actually, if you wanted, you could code this in NumPy. You could do gradient descent manually and all that. It would work. So here's just a summary of everything we said. No different. Could do this, but it turns out that because these computations are so well organized here, it's basically easy to construct generic software frameworks that can take any kind of computation graph and apply these things to it automatically. And so that's what we're going to talk about for most of the rest of today is we're not going to be coding this manually. We're just going to be coding this using PyTorch, which is one of these software frameworks that we essentially tell it, we communicate to it the structure of the network, and then it will do all of these forward pass and backward pass stuff. It will do this automatically without us having to worry about all these detailed derivations. So that's pretty nice. Okay, all right, so any questions on back propagation? Because I think that sort of covers all of it. It's good to at least know what is being done under the hood of these frameworks like PyTorch and TensorFlow and Keras and so on. Okay, so the very last thing we didn't really talk about yet is how to do this derivative. So just to be complete, let's talk about this. So we'll consider a couple more interesting cases, like what happens when we have binary cross-entropy loss. So we have then the overall loss is a sum over our batch elements of this guy, and we derived back in Unit 5 that when the labels are 0, 1, this guy looks like this. So now if I want to do dj dzoi, we can see, well, because we have a log, that's 1 over this times the derivative of this with respect to zoi, which is just this. And then add the derivative of this with respect to zoi, which is this. Okay, so this explains how that very first step would be done for binary cross-entropy loss. If you had more than 2 classes and you used k-ary cross-entropy loss, like we had in multinomial logistic regression, Well, in that case, we said that we would one-hot code the labels to these binary vectors. And in that case, we could write down the loss in this way. We derived this also in Unit 5. And so now you can see that taking the derivative of this with respect to ZOIK, again, because of the log, you have 1 over this. And then you take the derivative of the inside with respect to ZOIK, which gives you that. And then derivative of this with respect to ZOIK, which gives you that. So that would be, again, the first step in all these derivations, or right here. Okay, so that's it. That's all the ugly derivatives for backpropagation. From now on, we won't have to look at them again, at least until the next unit when we talk about convolutional networks. Then we'll take another look at them. Okay, and so the next thing to talk about is how do we actually implement this, since we're not going to be doing it manually by hand. So there's a whole bunch of different software frameworks that have been developed for this. This particular network, this website is just kind of an example of, saying what might be the top ones today. And so we have TensorFlow, that was developed by Google. PyTorch was developed by Facebook. JAX is also Google. Some of these other ones were developed by Amazon. So a lot of these big machine learning companies have developed their own framework. And one very recent one that I read about just a few weeks ago is that Apple now has its own framework that can leverage how its software or hardware architecture is done, which is kind of different. It doesn't have like RAM different from the RAM on the GPUs is the same as the RAM for the processor. So the way that you want to code for that hardware is actually different than the way you would code for most other hardware. So now Apple has its own framework. Anyway, so you have all these options, but the ones that are used the most, I would say, are these: TensorFlow, which was the original one from 2015. Keras, which is actually something that runs on top of other languages to simplify them. So you can run it on top of TensorFlow or Theano or CNTK. And then there's PyTorch. PyTorch is a little bit newer. By now, it's not very new anymore. So TensorFlow, being the original one, is in some sense the most mature, especially for deployment. What I mean about deployment is once you've kind of done all the prototyping and designed your method, you want to deploy this on many, many different software systems in the real world. And TensorFlow has a lot of very mature tools for doing that. Now, being in academics, that's not something that you guys as students need to worry about, or researchers really worry about. So we're more interested in just using the framework for prototyping, for research. So for that, Keras, what's nice about Keras is it really simplifies how things are done. So TensorFlow is kind of complicated. Keras makes everything super easy, almost too easy. So like if you want to program a neural network, you can do it in like a couple lines. And you're going to be doing very standard stuff. And the trouble with that is if you want to do something that's a little bit non-standard, if you're doing research, then you're not going to be able to do it in Keras. And if something goes wrong in Keras and you want to debug it, it's hard to figure out what's happening because of all the extra layers that have been put on top to make it simple. Now, so TensorFlow is very general. You can do just about anything with it. But it's complicated. The original version was very complicated. The newest version is less complicated, but still, from what I understand, pretty complicated. So PyTorch is an alternative that people find just generally a little bit easier to use. It's by now the most popular in the research and academic community, and I would say for teaching as well. So that's what we're going to focus on. It's just as powerful as PyTorch, it's just a little bit easier to use. And you can read articles about pros and cons and differences between these methods if you like. There's some links below. But what we're going to do next is we're going to go through sort of the standard recipe that you would use with PyTorch. It is a little bit involved because it's really doing quite a lot of things to make all this backpropagation and optimization and mini batching and all that. It makes it all easy, but there's still a lot of different moving parts. So we're going to go through these 5 steps. There are really great tutorials written by PyTorch that I highly recommend if you want to go deeper or if you want to get another view into this stuff. But okay, very first step, import the library. This is basically importing PyTorch, and then importing the specific tools that we need to handle the data. So that's the first step. So the first thing to talk about is a data type called torch tensors. So when we work with NumPy, we know that we work with these NumPy ND arrays, which are kind of like, you use them for vectors, for matrices. You can use them for tensors, which are like objects that have more than 1 or 2 dimensions, like 3 dimensions or 4 or whatever. And so when you work with PyTorch, torch tensors are kind of like the native basic building block that you use to represent numerical objects, like vectors, matrices, and tensors, and so on. What they have beyond your standard ND array is that they contain the gradient as well as the value of every number in your system, because they figure, this is going to be some variable within a computation graph, and you will eventually be doing backpropagation through that variable. And so, in addition to storing the value of the variable, you also want to store the derivative of some cost with respect to that variable. So when you define one of these torch tensors, it has this and the derivative there. And it is set up to use backpropagation when it knows about how that variable is connected to other variables in your network or your flow of data. So those are torch tensors. So you can see here, we start with NumPy quantities, but we then convert them to torch tensors. And we just give them slightly different names to remember that that's what they are. Now, these x, y's, these are the data, so the features and the labels as usual. We're going to tell PyTorch that this is formally a data set. So we give them to this object here, and then it knows, okay, this is a data set with features and labels. And then we give that data set to something called the data loader. And the data loader is what has all the support for, let's say, mini batching and things like that. So here is how we will eventually be using this. When you want to draw a mini batch of x and y's from your data, you put it in a for loop like this, for batch comma data in the loader. And so when you enumerate this loader, it spits out this data thing, and then from the data you can separate it into features and targets. So this is sort of what you get from this data set object. So that's nice, because then you don't ever have to worry about figuring out the different random indices you need for each epoch. All that is handled seamlessly without you worrying about it. Also, to support really large data sets where you cannot handle all the data on a single processor, there's all this other stuff that is done under the hood. Like if you have multi-processors, what it does is it farms out your data to multiple processors. So it does all this smart stuff that really does matter when you have big machine learning problems to work on. All right, so that's the first step. Next step, we're going to construct our neural network. So for here, we need to import the Torch neural network library, which has all the different pieces we need. And then this is how we implement, or how we represent a neural network. This is going to be an object-oriented sort of thing where there's some initialization code, and then there is the code for the forward pass through our network. So here, this initialization block will define some internal variables that are stored. So in this case, we're saying this is what the activation is going to be. It's going to be a sigmoid. You can see this is just one of the standard objects in the neural network library. Then the linear layer, you can see this is standard matrix multiply. It's what they call linear. You have to tell it what are the dimensions of that. Those dimensions are things that we will give this function at initialization time. And it will contain, this will make that first linear block in our network. Then we're going to make the second linear block with slightly different dimensions. So you can see the first one is going to take n input variables, and it's going to output nh hidden variables. Then the second one is going to take in nh hidden variables and output nout outputs. So we're going to use number of outputs 1 because as we go through this, we're going to be implementing that very first neural network that we motivated at the beginning. It was the one that that generated like that picture. So for that neural network, we have just one output, so that's what we use. So those are the main things here. This is our net. We have our forward function and this initialization thing. Okay, and then down here you can see this is when we instantiate it. We tell it, okay, create one of these things. We'll call it our model with nx inputs, nh hidden variables. Nh is going to be 4, and a single output. All right. Any questions so far? Okay. All right. So now we have to tell it what kind of optimization algorithm to use and what kind of loss to use. So it has a lot of optimization algorithms built in. The standard stochastic gradient descent is one of them, but it's not a very commonly used one because there's a lot of other fancier ones with additional tricks like adaptive step sizes and momentum and so on. The one that most people use as a first choice is called Atom. So that's the one we're going to use. And when you tell it which optimizer to use, you're saying, okay, use Atom. You also tell it which parameters it's going to be optimizing. And so model, which was this thing, dot parameters, tells it those are the parameters. It's going to be this, and this, basically. And now you can also give it any other things that affect that optimizer. So here we're going to tell it the learning rate to use. Anything you don't tell it, it will just use the default values. If you'd like to learn about all these different algorithms that are used for deep networks, there are some links I put in here. You can see what the difference is between them. But anyway, this is now we've told it which optimizer to use. And second, we have to tell it which loss function to use. So here you can see we're using the binary cross entropy loss, BCE loss. Other options would include cross entropy loss, MSE loss, which is for RSS, L1 loss, which would be, instead of using sum of squared errors, it's sum of absolute errors, and so on. And a cool thing about these loss functions is that you can literally scale and add them together, and it does just what you would hope. It actually scales and adds the actual losses. Okay, so that's what we've done in these lines. So now we know what loss function and what optimizer to use. Any questions there? Okay, and so this is the most involved block. This is going through 2 nested loops to train the model. So there's an outer loop over epochs, and then there's an inner loop over the batches within each epoch. A lot of this other stuff is just setting up we're telling it how many epochs to use, 2,000, but then we're setting up some other stuff that's going to, like every 100 epochs, it's going to print something out so we can keep track of how well things seem to be going as we optimize. And we'll set up some empty arrays to store some parameters that, or some, the loss and the accuracy that we see as we are optimizing, so we can plot them later. And then a few other things. We have like an error counter that's just counting how many binary errors we've made in our training data as we go through, and then as well as a total number of samples we've seen as we go through the epoch. Batch loss is another empty, initialized empty, and we'll eventually fill it. All right, and then the interesting stuff is happening in this inner loop. So these are the lines we saw earlier. So every time we go through this loop, it pulls out a single batch from our training data set, which we're extracting into X and Y components here. Now, sometimes you have to do a little bit of work to maybe reshape those things to get PyTorch to work with them. So in this data set, okay, so the X batch would come in as a matrix. That makes sense because you have, every row in that matrix is going to be a different element in your batch, and then across the columns you have the different features, which in this case, there's just 2 features. But then the Y batch, in this case, the way it's set up, it's just going to give you a vector, not a matrix. And it turns out PyTorch doesn't like that. It wants X and Y to both be matrices. So this step here is needed. Here we're reshaping that vector into a matrix with 1 column, and then it's happy. So there's a lot of these little things where sometimes you run the code and you just get this weird error, like it's complaining about something, and it's often about that Y is not exactly in the right format that it's looking for. Sometimes the issue is that it wants Y to be a floating point number and you've given it an integer. So that's another common thing that could be happening. So anyway, once the batches are set up, in this line, we put our batch of data through our model. So we're putting it through that forward pass, and you can see that we're getting this output. Now this output is, let's see. Okay, so this output, I believe, will be a torch tensor. And now we're going to give that output to our criteria. That was our loss function. And we're going to say, okay, that is essentially the outs are the predicted targets, and then Y batch is the true targets. And give those 2 things to the loss function to compute the actual loss. Now, this loss is not just a number. It actually is an object with a bunch of functions associated with it. If you want to extract the number, the actual numerical loss, you do loss.item, and then that extracts the numerical value, and then we're going to append that to our batch loss here to keep track of it so we can plot it later. But as we'll see, there's other stuff that we can do with the loss. Now, this is how we get ready for backpropagation. We tell our optimizer to 0 all the gradients. So set all the gradients to 0 so that when we do this backward step, loss.backward, it fills the gradients with the backpropagated derivatives. If you don't 0 the gradient, then they pile onto the ones before and you get the wrong numbers. So now we have done the backward pass. All the derivatives are stored internally, all the gradients. And now when you do opt.step, that says, have your algorithm take 1 step of something like stochastic gradient descent. So, so you can see these are all the kind of main steps. And that's most of it. Now, just for the purpose of keeping track of how many errors we've made, we're going to take the output here, and that's going to be a real number coming out of our network. Now we're going to round it, so it's going to be an integer, and that guess we're going to compare it to the true label in our batch. If it matches it, we'll get a 0 there. If it doesn't match it, we could either get a 1 or a -1, depending on the two values. So we're going to take the absolute value. So if there's an error, this thing will be 1. If it's no error, it'll be 0. And we can sum that and add that to our total error counter. So this total error counter will just be counting up the number of errors in all the different elements across all the batches we've seen so far within that epoch. And then total does the same thing with the total so that we can finally compute the accuracy over that epoch like this. We can also store the average loss over the epoch and the average accuracy. This is just storing the accuracy over the epoch. Okay, so this is just all the details of how you train the network. So you run this, in this case for 2,000 epochs. Any questions on any of this? Yes.
I missed this. Is it reshuffling the batches after each epoch, or where does that happen?
So every epoch you run this once, and this for loop will keep going until there's no more data in the training set. So yes, basically every time you so it's not like you have to tell it how many times to do the for loop. It just knows because it sort of uses up all the data in your training set, one batch at a time. And once it's all used up and you start over again, then it knows to reshuffle.
So it automatically does that?
It automatically does that, yeah. Exactly. Okay, any other questions? All right, there's a lot here, so you'll need to look at this on your own time. This is what happens if we plot the loss over the epochs. You can see it starts out big, it very quickly gets small, and then gradually it gets to some final value. And if you look at the training accuracy, that is getting up, in this case, almost to 90%. So once it's trained, we said we wanted to make this plot. So let's see. Basically, this code goes through how to do that. Essentially, the trick here is we want to evaluate the output of the network on a dense grid of possible values for x0 and x1. So we make a very dense grid of 100 by 100 different values. We essentially put each one of those pairs as the row of this matrix that's now going to have 10,000 rows, and we put that whole thing through our network. We will eventually get the outputs, and we're plotting those in this function. So that's what's happening on this page. I don't know if it's really worthwhile to go through all the details of how to do it, but maybe you can do that on your own time. So that's how we get this. You might also wonder, okay, how do you get these plots? So for these plots, if you remember, this was the hidden layer activations as a function of all those different X on that grid. And so for this, what's interesting is that we're not going to use the entire network we coded. We're actually just going to use pieces of it. We're going to take that matrix with 10,000 rows, and we're going to put it through model.dense1. So we can just kind of use that piece in isolation, put the data through there, and then put the output of that through model.activation. So now we're kind of going halfway through our network, and that's something we can do. And that's eventually how we plot those plots. And then to get the values of the weights that you see printed here, we can extract the trained parameters using something called the state dictionary of the model. So we basically get the state dictionary, and then the state dictionary, from that we can extract the different parameters like the weights of dense 2 and weights of the bias of dense 2 and so on. Okay, so that's how we did that. Any questions there? Okay. And so then we essentially took that 2-layer network, and we can apply exactly the same network for MNIST the only thing we need to do is change some dimensions. So rather than having 2 features, we now have, I'm trying to remember how many it is. I think it's 384, however many pixels are in those MNIST images. And instead of having a single output, we have 10 outputs because we have 10 classes. Instead of having a binary cross-entropy loss, we would have the just the cross-entropy loss. I think that's it. Is there? Oh, I guess one slight difference. Instead of having the last activation be a logistic sigmoid, it needs to be a softmax. So you make a few changes, and you can apply essentially almost the same thing to MNIST. And in this case, we have 50,000 training samples, and run this, and we get a test accuracy of 97%, which is pretty good because that's what we got with our support vector machine classifier, or the radial basis one, the good one. And so this is a very primitive neural network. It's just, it's definitely, we could do a lot better if we tried. And also, it's much faster to apply this once it's trained. If you run your support vector machine, your RBF classifier, even after it's trained, you find that it has to use all the different support vectors. And if you have, 50,000 training samples, there could be a huge number of support vectors in there that it has to go through just to classify one single test image. So that's very computationally expensive. This one, you just take that test image and you just push it through the network, and it happens almost instantaneously because there's really just a couple matrix multiplies to do and some simple scalar nonlinearities. And so it's orders of magnitude faster. This is the plot versus epochs of training accuracy. You can see the training accuracy is getting close to 100%, and the test accuracy here is getting up to 97. So when you have a capable enough neural network, it's almost expected that the training accuracy gets perfect or nearly so. That's typically how you want to run these things. From the classical perspective of bias variance trade-off, you would say, well, this thing is overfitting in that it's doing really well on training, not doing as well on test. But if you so the way that you could make this worse for training is you could use less than 100 hidden nodes. If you do that, this will come down, but I don't think that this will go up. So it's not like you need to match these. It's good to know that your network can do perfectly on the training data because that means there's essentially no bias. And it's also doing quite well on the test data as well. Okay, so that's applying this to MNIST. Any questions there? So this is probably one of the most important design questions is how many hidden nodes do you use? 4, which is what we used before, would definitely not be enough. That would not work at all. But in this case, 100 seems to be enough. Okay, and just to comment on that, whenever you do this for a new data set, there's a number of different things you need to choose. So, for example, very importantly, you need to choose how many hidden units. That's going to have a huge impact. At least if it's too small, it's going to kill everything. You need to choose the type of hidden layer activation functions. Are they going to be sigmoid, tanh, ReLU, something else? You need to choose which optimizer. We used Atom, but you could use a different one. You need to choose the learning rate. That's going to have a huge effect. If the learning rate is too small, what happens is you will get stuck in a local minima and it will never escape. If the learning rate is too big, it will just bounce around crazily and it won't converge to anything. You want it to be somewhere in the middle. You can also be more sophisticated, and you can start with a big learning rate and then decrease it over the iterations. That's called scheduling it. You need to choose a batch size. The batch size, number one, it just needs to fit in memory. More than that, if the batch is, there's sort of an interaction between the batch size and learning rate, as we've seen. So the smaller the batch size, the smaller the learning rate needs to be. So if you're playing with this, you can't just change the batch size without changing the learning rate. You'll come to the wrong conclusions. But those two things can be individually optimized. And then you'll need to choose the number of epochs, obviously. And generally speaking, you just want to use as many epochs till you see things settling out and looks like no progress is being made. Now, there's other things that you can do to enhance performance. One is L2 regularization. What's interesting about when you use L2 regularization in deep neural networks, it has a kind of surprising effect, which is rather than just shrinking the values like we saw in linear regression, it actually, because of the nonlinear activations, it actually sparsifies the weights. It makes a bunch of them zero, kind of like what Lasso did. So it works differently in the context of neural networks than with linear designs. And the way to do L2 regularization, it turns out you do that via the optimizer. It just has a parameter called a weight decay, and you just set that, and that does the L2 regularization for you. Okay, one final comment, I think this is pretty much the last thing, is there are packages out there, Optuna is one of the most popular, that you can use to tune all of these things if you have enough compute. So basically you just say, I want you to try all these combinations of all these variables, and I want you to just run for like a week or whatever it is to try to figure out what is the best combination. And it's smart in the sense that it will try things in a smart way, and if it seems like it's not working, it will kind of give up, and it will focus on things that work better. So you're welcome to use this for the final project. What I've seen, based on previous semesters, is that this can give you very good designs, but if you use it in a foolish way, it can give you quite terrible designs. If you stop it too early, or if you, things like that. On the other hand, if you, just as a human, use your intuition and engineering sense to go through and tweak all these things, one by one or maybe in pairs, you can also come up with really good designs. And I would say almost in an equal amount of time. You can do this manually and get a good design, or you can do this in a smart way, but it will take a lot of processing power. And either way, you can get good designs. So you're welcome to use both for your final projects. So the very last thing I want to say is that, I think I've said this before, is that there's a couple options with how you design your networks. You can either use a final activation or not. You can just, you can conclude your network with putting out linear scores, or you can put on an activation, but the activation must match your application or your task. So if you're doing binary classification, you must put on binary cross entropy, or logistic sigmoid. If you're doing classification with more than two classes, you must put on a softmax at the end. Now, once you've done that, you must also use the correct loss in PyTorch that matches what you did with your network. So, for example, if you're doing binary classification and your network has no sigmoid at the end, it just puts out Z, you have to use this thing called BCE with logits loss. On the other hand, if you put on that activation function at the end of your network, then you must use BCE loss. And if you're doing multi-class classification, more than two, and you conclude your network with Z, then you use cross-entropy loss, but if you put a softmax at the end, you must use NLL loss. So you just have to be aware of, be consistent and be aware of all these options to use. If you mix and match incorrectly, basically it just won't work. I mean, it will run, it won't give you good performance. So that's all I have to say for this unit. Any last questions? Okay, so this is pretty fun. It's very practical. You can solve a lot of really cool problems with neural networks like this. So have fun with the lab.